In this video, we will analyze the noise power that is at the output of different filters. And it is necessary to filter the noise to limit its power, because remember that the statistical model for the thermal noise is a wide Gaussian stationary anergodic random process with zero mean and with constant power spectral density, constant value n0 halves, where n0 is the product between the Boltzmann constant and the temperature in Kelvin degrees. As for any wide process, theoretically, the power of the thermal noise is infinite. The integral of the power spectral density is the integral of a constant value, and this integral is equal to infinite. Because of this, it is necessary at the input of the receiver to filter to limit the noise power. And now we are going to see the power of the noise that is at the output of different types of filters. We will start considering ideal filters. Ideal filters with a given bandwidth, bHz, or equivalently W equal to 2 times pi, the bandwidth in hertz, radians per second. The noise power at the output of ideal filters will be the same one for low pass or band pass filters. This is the frequency response of a low pass filter of bandwidth W radians per second, and this is the frequency response of an ideal filter band pass with the same bandwidth. The filtered noise will be denoted by Z of t, and the power spectral density at the output of the filter is the power spectral density at the input, n0 halves, the power spectral density of the thermal noise, times a square modulus of the frequency response of the filter. Taking this into account, now the power of the filtered noise can be obtained by integrating the power spectral density. And this integral is equal to n0 halves times the integral of the square modulus of h divided by 2 times pi. If we integrate this shape over here, the integral is 2 times w divided by 2 times pi is 2 times v, and the same thing happens here. The integral of this part is w, the integral of this part is w, 2 times w divided by 2 times pi is 2 times v. So, both for low pass or for band pass filters, the power of the filtered noise is equal to n0 times the bandwidth in hertz of the ideal filter. If now we consider ideal filters but with a given gain, the power gain is G, this means that the voltage gain is square root of D. Here we have the frequency response for a low pass filter and the frequency response for a band pass filter. With respect to the previous case, the only difference is the amplitude of the response in the band pass, that is the square root of G, the voltage gain. If we repeat the procedure, the power spectral density of C is just n0 halves times square modulus of h, and then in the integration, the previous result is times g in this case, because now the integral of the square of this response is 2 times w times g divided by 2 times pi is 2 times v times g, and the same thing happens for this part. The integral of this part is g of the square of this response is g times w. In this part we have another term, b g times w divided by 2 times pi, we have the same result. And in any case, the power that we have at the output of an ideal filter, low pass or band pass, with a bandwidth bHz is n0 times this bandwidth bHz times the power gain. This is a very well-known result and is applied in many occasions. With ideal filters, the power of the filtered noise is n0 times the bandwidth in hertz times the gain of the corresponding filter. With non-ideal filters, it is necessary to take into account the frequency response of the filter. because if we have this power spectral density and 0 halves times square modulus of h of j omega, the power will be obtained by integrating the power spectral density, and we will have n0 halves times the energy of the filter, because the integral of square modulus of h by the Parseval relationship in the frequency domain is equal to the energy of the filter. In many cases, to avoid the users to evaluate the energy of the filter, the manufacturers provide the noise equivalent bandwidth. This is a parameter that is usually provided by the manufacturers that allows to compute the power noise at the output of the filter in a very simple way, and in a way that is very similar to the power with ideal filters. The expression to obtain the power is n0 halves times this noise equivalent bandwidth times the gain of the filter. This is equivalent to the analytical expression for the noise power for ideal filters. Taking this into account, and taking into account that the gain of the filter is typically defined at the maximum value of the square modulus response of the filter, it's straightforward to obtain the definition for this noise equivalent bandwidth. Because if we go back to this expression, we just need to equate this expression to this expression, and 0 here and then 0 here will cancel, and then solving this equation for the equivalent noise equivalent bandwidth, we obtain this straightforward expression: the energy of the filter divided by 2 times the gain of this filter. And the energy can be computed both in the time or the frequency domain, taking into account the Parseval relationship. The noise equivalent bandwidth has the following interpretation: the noise at the output of a given filter is equal to the noise at the output of an ideal filter, with the bandwidth equal to this noise equivalent bandwidth and with the corresponding power gain.